I was just thanking Raphael and the organizers for inviting me, and it's a pleasure to be here. And as I was saying, I'm going to be talking about two new approaches to improving the efficiency of converting solar photons into photovoltaics or into solar fuels. Solar fuels are very important. They're not as far advanced as photovoltaics, but something like 3/4 of the energy consumed globally is in the form of liquid and gaseous fuel. It's currently produced from either refining fossil fuels or from refining biomass. And what we mean by solar fuels now is to produce these fuels either by artificial photosynthesis, which is reducing carbon dioxide with water to make carbon-based fuels, which can be, when they're used, generate CO2 again, but it's a closed loop, so you don't increase the net concentration of CO2 in the atmosphere. And a lot of the physics and chemistry involved in photovoltaics is the same for solar fuels, but the problem is much harder because of the tendency of photoexcited materials to undergo photocorrosion when they're in contact with liquids, which is generally the approach used for producing solar fuels. The approaches will be based on the idea and a concept that we developed at NREL about 10 years ago, and which has subsequently been confirmed by experiment, which is that you can produce more than one electron-hole pair from an absorbed photon in nanostructures like quantum dots, quantum rods, and other nanocrystal forms. And that's called multiple exciton generation because in these structures, the electrons and holes are confined to very small regions of space. So you have very strong quantization effects which couple the electrons and holes so that they don't exist as free carriers like in a bulk semiconductor, but rather exist as excitons. And in those quantum dots, as we'll see, it's possible to have very efficient generation of these multiple electron-hole pairs or excitons, which can then be split into free carriers to either generate electrical power or using those carriers to carry out electrochemical reactions on a surface to generate hydrogen by water splitting or to oxidize and reduce water in combination with CO2 to make fuel. So I come from, I've been here since the late 70s, and this institute, when it was first started, it was called Solar Energy Research Institute, started by President Carter in 1978, which is when I joined that institute, called SERI, Solar Energy Research Institute, and then the name was changed by the first President Bush in 1990 to National Renewable Energy Lab, and it became officially one of the national labs of the United States, run the same way as Argonne, Brookhaven, Sandia, Lawrence Livermore, Berkeley. There's about 11 national labs, and so we're one of the newer ones. But we've had a very varied history in terms of support. So President Carter, who was actually a nuclear engineer, so he was technically trained. So in the 70s, he understood that the United States and the rest of the world need to transition from fossil fuels to renewable fuels and power and energy. And so he started this institute, and it grew in 1978 from 0 people to 1,200 people in about 2 years. So it grew very rapidly. And then President Reagan was elected, and he's a conservative, and this is generally the case that renewable energy is very political. The support from the government, maybe it's true here in Canada, depends on who's in power in the United States, in the White House, globally, who's in power in other administrations. So President Reagan and his supporters, who are mainly from Texas and the fossil fuel industry, is not inclined to support renewable energy because they have a vested interest in keeping things going with fossil energy. I think you have a similar situation here in Canada where you have very rich resources of fossil energy. So he campaigned on the promise of closing down the Solar Energy Research Institute. He didn't succeed in closing it completely, but he did succeed in reducing the population of the lab from 1,200 people in 1980 to about 400 people by 1981. And it's gone up and down over the years, and most recently with President Obama in office, being more to the left, he's in favor of renewable energy, and so the lab grew to a size which is about 2,500 people, and that's the way it is now. And we have a lot of new construction based on the stimulus package in the States. A lot of the money went to build infrastructure in various places, including NREL. So the motivation for doing this kind of work is based on the fact that in order for renewable to be competitive with fossil energy, which intrinsically is very cheap. I mean, to extract a barrel of oil, at least in Saudi Arabia, it's only a few dollars per barrel, but yet the cost is more like $100, and the rest is essentially profit. So what the problem is for renewables is that as the technology develops and it becomes competitive with the fossil producers can always cut the price and still make very big profit. And in order to be competitive with fossil energy, you have to have a combination of very high efficiency of converting solar photons to other forms of free energy like electricity or chemical bonds and fuels, and low cost. And as we'll see, the figure of merit is the ratio of the cost per unit area divided by the power that you get from the converter per unit area. And that gives you dollars per watt, and it's rated, solar panels are rated at peak watts, which is how much power you get from the solar panel at high noon with no clouds. And you can define these three generations. This is third, or more preferably called third generation. So the first generation is what is commercially available. It's mainly based on silicon, either single crystal or polycrystalline silicon and some amorphous silicon. And this is a plot of the efficiency, which is percent, but since you get 1 kilowatt per square meter with no clouds at high noon, you can just multiply this fractional efficiency by 1,000 to get watts per square meter. So if you divide dollars per square meter by watts per square meter, that gives you the inverse slope of this line, and labels, you get a number which is how the panels, say for PV, are rated. They used to be about $3.50 per peak watt, because on average the cost was $350 a square meter, and 10% efficient, that would give you $3.50. You could convert that to cost per unit of energy which takes into account cost of capital, the cost of maintenance, depreciation, the lifetime of the panel and so forth. But if you multiply this number by 0.05, that gives you the dollars per kilowatt hour, which is what consumers are used to considering. That's what you pay the power company. But there's been a dramatic change in the economics of solar PV over the past 4 or 5 years, driven by China, which is producing. They came out of nowhere. I mean, 6, 7 years ago, China didn't produce anything. Now they're the #1 producer of solar panels, and they are producing and selling these panels at very low cost, which are approaching less than $1 a watt. And this has caused turmoil in the market because many companies can't make a profit at panel cost of selling price of $1 per watt, and so they've been going bankrupt. So many of the big companies in the U.S. and some in Europe, and even the biggest company in China has gone bankrupt because that's Suntech, because they can't make a profit when they sell these panels at such low cost. So it's ironic because the goal of the research is to lower the cost, but the cost came down so fast and the production increased so fast that there's an oversupply of low-cost panels, and this is good in the long term, but in the short term, it's not allowed companies to be profitable who are in this area, and it's caused this turmoil in the marketplace. But in the end, it'll all straighten out, and I think renewable energy in the form of photovoltaics and solar fuels eventually will become competitive with fossil and with nuclear. To do that, you have to be in this area here where the cost would be maybe $100 to $200 a square meter, and the efficiency would be greater than 50%. That's above this, what's called Shockley-Queisser Limit, which is a thermodynamic calculation done by Shockley and Queisser about 1960, which indicated with certain assumptions which are not cast in stone. You can get around these assumptions. They're not unavoidable. To get an efficiency above 50% at a cost of $100 to $200 per square meter will give you a cost of PV or fuel which is going to be competitive and even cheaper than the cost of coal and natural gas. So these future generation technologies, which are, the conference called Next Generation, people who are in the business don't like it to be called third generation because it implies the first 2 generations are passé. So some of the funding agencies are not supporting first and second generations because they think the third generation is going to displace them in the near future, but that's really not the case. These are longer term prospects. The second generation are the thin films, which have about the same efficiency as, say, amorphous silicon, and in some cases even crystalline silicon. In some cases a little bit higher. So they're about 10 to 15% efficient with lower cost, but they don't really change the cost of the energy per kilowatt hour that much, maybe a factor of 2. But to get the real gain, where you need this very high efficiency above the Shockley-Queisser limit with a very low capital cost, that's the goal. So there are many approaches to doing this, and there's a couple of books by Martin Green and Antonio Luca called Next or Third Generation PV, which describe these other approaches, but today I'll just talk about using quantum dots and molecules, because the idea that you can generate more than one electron hole pair per photon has an analogy in certain molecular chromophores. And so this is of great interest to chemists because you can develop and employ molecules which will absorb light and do the same thing in terms of producing more than one electron per photon. So the idea that you can do this is old. It actually does occur in bulk semiconductors. It's called impact ionization, and it was studied 40 years ago in many bulk semiconductors. And in that case, to conserve energy, of course, the photon has to be at least twice the band gap And this extra energy, which is in the form of kinetic energy of the electron in the hole, can, instead of cooling, which is emitting phonons and converting this excess kinetic energy into heat, can do something more useful, which is to generate a second electron-hole pair. But this process in bulk requires that not only do you conserve energy, you have to conserve momentum. And to conserve momentum, you can show, and it was shown very early, that it requires a very high energy photon, which has an energy that's outside the solar spectrum. Typically, it's 4 to 5 times the band gap of the semiconductor. So for silicon, the photon energy required to generate multiple electrons per photon is above 3.5 eV, which is outside the solar spectrum. So it's useless for solar energy conversion because those photons don't exist in the solar spectrum. And the conservation of momentum is shown here, that you have to excite high in the band, in the conduction band of silicon in order to have the change in momentum of the electron exciting, or it's called impacting an electron in the valence band to excite it across the gap. Those two vector changes have to cancel each other, and that requires this high energy photon. But when quantum dots, you have some new physics that arise. First of all, you don't have to conserve momentum, just energy, because you can think of it in the simple terms that when you confine the electron in the hole to a small region of space, according to Heisenberg uncertainty principle, you know where the electron is, therefore you don't know the momentum. So momentum is not a good quantum number, and you relax the requirement to conserve momentum. Secondly, because you have the electrons and holes very close together, these quantum dots are typically 1 to 10 nanometers in size, which means that you enhance the Coulomb interaction between the electron and the hole way, way above what occurs in free carriers in the bulk material. And the multiplication process is a type of Auger process, and so it's enhanced in quantum dots. Secondly, the competing process for those high-energy electrons and holes created by the absorption of a high-energy photon is the emission of phonons, which produces heat. And so that's where something like 50% of the energy coming in from the solar photons is lost because you convert the high-energy electrons and holes created by the high-energy photons of the solar spectrum into heat. And if you can avoid that by either using those photons to generate more electrons or to extract the hot electrons before they emit phonons and cool to the lattice temperature, you can increase the efficiency quite dramatically. And for the case of extracting them, which I won't talk about, but this is where we started looking at this, is these so-called hot carrier solar cells. The efficiency calculated using the Shockley-Queisser approach, but assuming that the electrons don't relax or cool by phonon emission, but are extracted faster than the phonons and electrons can interact, can produce efficiencies above 65%. So you more than double the Shockley-Queisser limit with a hot electron or a hot carrier solar cell. And so there is work continuing in this area, and there's been some progress. But the other approach that looks very good and works is the one I mentioned, which is to use the excess energy to produce more electrons. So you get a higher current. In the hot carrier case, you get a higher voltage with the same current because you're not multiplying electrons from the absorbed photons. But in a quantum dot solar cell, you have the same voltage. It's changed because the quantization increases the band gap, so you can control the band gap of the same material by just controlling its size and thus its voltage. But you get this increase in current. And then finally, there's a very interesting effect when you use solar concentration with carrier multiplication. You get a huge increase in efficiency, which approaches about 80% when you're up around 500 suns or 1,000 suns. So this was the idea. It was first proposed in 2000 or so, that in a quantum dot you slow down the cooling, which is the electron-photon scattering, by having discrete states that arise because of quantization in the quantum dot, which typically, as I say, is between 1 and 2 nanometers. Because you have in the bulk, you've got a quasi-continuum of energy levels, and you can relax the hot electrons by interacting at one phonon at a time. But in a quantized system, you have this fairly large spacing between energy levels, and you need many phonons simultaneously to interact with the electron in order to make the transition from one state to the next. So you slow down the cooling. You don't have to satisfy energy or momentum conservation. These two factors led to a prediction back in, say, 2002 or 2001, that you should have a higher efficiency of multiplying the carrier production from absorbed photons and quantum dots. And as I mentioned, in quantum dots, you can change the band gap just by changing the size. Unlike bulk materials, to change the band gap, you have to change the material. But in the quantum dot, you keep the material the same, just change its size, and you get very large blue shifts in the absorption, which corresponds to changes in the band gap. And this depends primarily on the effective mass of the material. So this just shows the competition of the relaxation of these high energy or hot carriers. In this case, I'm just focused on the electron. In the bulk, you excite, but it can undergo these cooling, and it's very fast. It's about a picosecond or less to go from the high energy state to the bottom of the conduction band, and you emit one phonon at a time. And the impact ionization is this process here, which cannot compete with the cooling unless you have a very high energy photon. But in a quantum dot, you can slow down the cooling because of these discrete states, and therefore the rate of multiple exciton generation, which we call MEG or MEG, can be competitive with the cooling rate, and indeed it does. Now, there are various characteristics that could be conceived. One is the ideal case where every time the photon energy is n times the band gap, you get n electron hole pairs, or n excitons. And you do this as the photon energy increases, you would get a staircase type function. So I'm plotting the quantum yield of electron hole pair production versus normalized photon energy, which is how many band gaps of energy you're exciting with. But until recently, we were just beginning to close in on this staircase type behavior. Most of the data in the literature shows that you don't have a step-like function, you have a linear function. So there's a threshold after which, for the multiplication, after which you get a linear increase in the quantum yield versus photon energy. And we showed in this paper that the threshold is related to the efficiency. The efficiency is the slope of the line. It tells you how many electron hole pairs you get per additional band gap of excitation beyond the threshold. The best you can do is a threshold of 2. If you have a threshold of 2, you'd have 2 electron hole pairs produced when you're twice the gap. And then as you go to 3, you'd get 3 and so forth. 3 electron hole pairs, and so there's this simple relationship between how many electron hole pairs you get per photon when you're beyond the threshold, and that efficiency is simply related to the threshold energy. So you don't need to; these are not independent parameters. And when we do the Shockley-Queisser analysis, shown here in this paper, both for PV and for solar fuel productions, you see that you get this significant increase in the maximum possible thermodynamic conversion efficiency compared to what you get in the Shockley-Queisser limit, where you assume that the electrons thermalize and don't use that extra kinetic energy to do useful work. And then for the various types of characteristics I showed, you get different Shockley-Queisser type plots. And you can see very quickly that in order to get a significant increase in the efficiency, you have to have an onset for this process that's at less than about 2.5 times the band gap. The best is the staircase. And this represents about a 35% increase in efficiency, which is quite good. Now, the way this is measured is there's 2 ways to do it. One is to use ultra-fast time-resolved spectroscopy. So it's a pump-probe experiment where you pump with the big high-energy photon, and then you probe with a probe beam, which in which you measure the photo-induced absorption of an electron that's in the bottom of the well, which is the 1s state, to the next state, which is a 1p state for the electron. Or you can use photoluminescence or terahertz spectroscopy. There's various ways to pump and then probe using spectroscopy to determine how many electron hole pairs you have. The most direct method, this is indirect because you're looking at how the population affects light. So you're not counting the electrons like you do when you measure the current. So if you measure the current, you actually count the electrons. And that's the most direct. And we showed just recently, about 1.5 years ago in this paper in Science, that for the first time in a solar cell, you can measure a photocurrent quantum yield that has a value greater than 100% within the solar spectrum. So this is typically the kind of data you get. The signature of the multiplication process is an early time fast decay. So when you're below the threshold, the decay is just a slow recombination, usually non-radiative recombination, which is hundreds of picoseconds. But if you have 2 excitons in a quantum dot, they can undergo fast Auger recombination, such that you get this, as you can see here, as you increase the energy of the photon in terms of how many band gaps of energy that photon represents, you begin to see this fast component growing in, and the higher the amplitude of that early time component versus how long it takes to decay to its till the Auger produces just 1 electron hole pair, you can determine the population. And so that just shows data that was reported. It was first reported by the Los Alamos group led by Victor Klimov, and they sort of found it accidentally. We were looking in the 3.5s for this, but didn't see it. It's harder to see. It's very easy to see in the 4.6s, like the lead compounds, lead sulfide, selenide, telluride. But the data was scattered all over the place. This led to a controversy in that people either could not reproduce these results, or when they did, they said it was a small effect. And it turns out that this is due to variations in the surface chemistry between groups who are looking at this, because the surface in a quantum dot is a very high percentage of the total atoms in the quantum dot. So if it's 5 nanometers or so, it's 30% of the atoms are on the surface. So surface chemistry plays a big role in determining the effect of, or how the relaxation dynamics goes. Secondly, there's an effect also when you have a high energy photon, you have a probability of trapping it on the surface. And if it gets trapped, if that electron gets trapped on the surface and is long-lived, then when the next pulse comes along, the pump pulse, it'll see not a neutral dot, but a charged dot. And that charged dot also has an Auger-like characteristic, and this confounds the results. So that's just shown here. When you start, at this point with a neutral dot, you excite it with a high energy photon. You want this extra energy to produce 2 excitons, and then this will decay slowly over maybe a nanosecond by non-radiative recombination through surface states to a single exciton. But in some cases, this electron can be trapped at the surface, and then when the pulse comes in, it'll see a trion. It'll see it'll create a trion. It'll have an electron on the surface, and then you create another electron hole pair, and this also undergoes a fast decay, which can confound the signal. So the way to get around this, and this was explained in these two papers, the way to get around this is to do a dynamic experiment by moving the sample, either spinning it, stirring it, so that whenever when the pulse comes in, even if there's a trapped electron, the pump sees a fresh volume of a sample, and therefore it doesn't see the charged quantum dots, and then you'll get the right answer. So all that scatter, as we show in this paper here, which is a collaboration now between Los Alamos and NREL in one of these DOE Energy Frontier Research Centers, got rid of the scatter and showed you can indeed in different labs get the same result, and it confirmed that this is a real effect, and the efficiency is much higher compared to bulk semiconductor, which has an efficiency about half of what the efficiency is of the quantum dots for the multiplication process. And as we'll see in a second, or a couple seconds, when we do the photocurrent experiment, which was, I said, reported just about a year and a half ago, that data, which is quite robust because you count the electrons, shows that the quantum yield, if in this simple experiment where you just count how many photons are coming in and how many electrons are coming out, so you don't even correct for reflection, it's the external quantum yield, is a greater than 100%. When you correct for reflection and model the absorption characteristics of the quantum dots, you'll see that it matches the optical spectroscopic experiments. And so that's satisfying, and it means if you do the optical spectroscopic experiments correctly by having a dynamic experiment, you can get the right result, which is consistent with the photocurrent measurements. Now, as I said, we need the step function to get the highest efficiency. And currently, this is bulk material, which is way down here. And experiments are slowly moving toward the step function. To get the step function, it was shown in this paper that you need to have the ratio of the cooling rate to the MEG rate to be about 1 over 10,000. And that'll give you the staircase step function. Currently, we're about 10, so we're getting close, but not quite there, to get the step-like function. And size matters. So it turns out if you just have single crystals or three-dimensional crystals, nanocrystals, you're in this region. But if you go to elongated or nanorods, you improve the efficiency plot versus photon energy sufficiently so that you begin to get the staircase. Another controversy that arose in those days was that the people who were skeptical about this effect, this usually happens in science when there's some new phenomena that's reported, there'll always be, and that's good for science. I mean, there'll be a part of the community that's skeptical, and you have to get reproducibility in these experiments. But they also said that in their experiments, when you plot the quantum yield versus absolute photon energy, it turns and compare bulk to quantum dots, the data fall on top of each other. But that's not the right way to do it, because you need to divide by the band gap to tell you how many band gaps of energy you have being absorbed. That's the more fundamental parameter as opposed to absolute photon energy. But even if you plot for silicon, you can get very nice quantum dots of silicon, perfect crystal structure with no defects, either in the bulk or on the surface. Even when you plot it, in this case we're plotting it normalized, and you see it's much better than the bulk, which we saw before. Nothing happens until you're outside the solar spectrum. Here you see that you begin to get very efficient MEG at a lower photon energy relative to band gap, and that's a good thing. And even if you plot it on an absolute scale, you still can see a threshold earlier than the bulk and with a steeper slope. And more recently, these new results show that we're, as I say, beginning to approach the threshold of 2. So just in the past few months, we have some new data with isolated silicon colloidal dispersions of quantum dots showing that there is a step change in the quantum yield just when you hit 2. So if the photon energy is 1.98 times the gap, you just get a quantum yield of 1. If it's 2.02 times the gap, it jumps up. Now, ideally, you'd want it to follow this staircase function, but in the red squares are what we actually found. So it's beginning to show some of this staircase-like characteristics, but it's still not yet equal to a step function. I'll skip this, but this is an interesting result published by a group in Holland, that when you make silicon quantum dots in a silica matrix, an amorphous matrix, you also get very efficient MEG that has an onset of 2. And what's very interesting in that result, which is this paper here in Nature Photonics of last year, that they say they see the appearance of the 2 excitons immediately in 2 separate dots. This was a big surprise, because our belief was that first you have absorb the high energy photon, you create 2 electron hole pairs in the same dot, and then they separate in your device to give you 2 excitons that are separated, and then you break the excitons apart at the interface with the, say, ohmic contact, or in the junction, p-n junction, nanocrystalline p-n junction in the cell, and then you collect the carriers. But this direct mechanism is very interesting, and the process is very efficient. So this has to be followed up to see what that means. So as I mentioned, there is various ways to use these quantum dots in solar cells. One is to use them as a sensitizer, like in a dye-sensitized solar cell, which is called sometimes a Gretzel cell, because he was the first to show this works pretty well. These dye cells have efficiencies of about 10 to 12%, which is about, it's closing in on silicon, and it can be very cheap because it's not a high temperature process to make these, as opposed to the first and second generation, where you need to melt the silicon and grow single crystals or produce it from the vapor phase at high temperature. These are low temperature processes, which is one of the advantages of the third generation approach, including the organics. You can do these at low pressure with simple high-speed roll-to-roll processing. Or you can have a hybrid cell where you immerse the quantum dots into a matrix of either C60 with a hole-conducting polymer, or generally have 2 phases where the dots are dispersed, and then when you excite the dot and create multiple electron hole pairs, you collect them in the 2 phases. So this would be the electron conducting phase and the hole conducting phase, and you can build a device that way. What we've been focused on are these arrays, where you self-assemble the dots into an array. It's something like a PIN structure, where the I region is an array of insulating quantum dots, And this can be made simply by first you make the colloidal dispersions using simple chemistry, and then they self-assemble just by spraying or evaporating in a simple process to produce generally a disordered array. There are some regions which are ordered, but these are small regions of the structure where you have crystalline order, but on a macroscopic scale it's disordered. And if we make a solar cell simply by depositing, say, N-type zinc oxide quantum dots first, by evaporating a solution of zinc oxide nanocrystals with a second layer of lead selenide quantum dot nanocrystals, we get what we define as a nanocrystalline p-n junction. And when we measure the quantum yield and model the optics of this solar cell, you can see that there's a region here where we get a quantum yield greater than 100%. Now, also, no solar cell today has an efficiency quantum yield greater than 100%. So this is CIGS, cadmium silicon. The best that can be done is this silicon cell textured surface has a quantum yield of 100%. But over here with these quantum dots of the lead selenide, we can get a quantum yield greater than 100%, approaching 135% when you correct for reflection. And you can see that there's still a loss in the cell because there's normal electron-hole recombination even before you reach the threshold. The threshold's about here at about a little less than 2.6. And this just shows when you plot, this is the raw data, but when it shows that you're getting 15% loss in the cell just due to normal electron-hole recombination on the surface. If you correct for that, you get data for the quantum dot cell, which undergoes MEG, which has an efficiency of when you're like 4 times the gap, it's 130%. And that just says the same thing. So the efficiencies of these cells is about 4 to 5%. There's work here in Canada at the University of Toronto by Ted Sargent's group, and they're making these quantum dot solar cells, which now have efficiencies of, just reported about 2 weeks ago, of 8%. And then when you, that's without MEG, or they didn't look for MEG. It may be there, but they didn't report it. But you combine MEG plus, well, MEG may be present, but in the ideal case, if you could get MEG, put an onset of 2 times the gap with the staircase, you would have theoretical upper limit of about 46%. The theory of how this works, I'll skip this because it's, we don't have time, but it involves a superposition of states. And the general idea is when you excite with a photon with an energy which, say, 3 times the gap, you have other states which are degenerate with it, which are multi-excitonic. So this state has the same energy. It's degenerate in energy with this state. So there's 2 excitons. One of exciton has an excitation energy of 1 EG. So in all 3 cases, you have, say, 3 excitons with 1 EG, or 1 exciton with 3 EG excitation, and 2 excitons, one of which has 2 EG excitation and the other 1. So they all have 3, and therefore you have a coherent superposition. And it's the dephasing which determines how many you get. And when you have this asymmetric structure, this dephasing time dominates, and you're left with 2, breaks the coherence, and you're left with 2 excitons per photon. As I mentioned, I'm going to stop in a few minutes. If you combine the carrier multiplication with these various characteristics that I defined earlier, and this is bulk. All semiconductors will have a higher efficiency if you concentrate the light. It's essentially like making the sun bigger in the sky so that the re-radiation loss is lower and the back dark current is not increased very much, and the photocurrent is increased, so you get a gain in efficiency with increased concentration. But a normal solar cell or a quantum dot solar cell that has an onset that's greater than, say, 3.5, acts the same as bulk material. There's nothing to be gained there. But the efficiency for a normal solar cell goes from, theoretical efficiency goes from like 32% at one sun to maybe 40% at, say, 500, or 42% at 500 suns. But a quantum dot with the staircase, or the L2, gives you efficiency of like 75%. These are theoretical thermodynamic efficiency. So there's a huge gain in efficiency when you combine carrier multiplication or exciton multiplication with solar concentration. So this is a very important area to examine in the future. And the Shockley-Queisser analysis shows that the optimum band gap shifts far to the red. So these red dots represent the peak of the Shockley-Queisser analysis, and shows, well, if you had a band gap of 0.2, that's when you get the highest efficiency, and that's really small. But the idea is that 0.2 could give you 10 electrons per photon. If you take the average energy of a photon in the solar spectrum as 2, and the band gap is 0.2, that means a photon with 2 energy can give you 10 electrons. So we'll skip some slides. I'll just spend a minute or two on singlet fission, which is the molecular analog, so the chemists in the audience will be interested in the fact if you have a molecule where the triplet state is about halfway between the ground state and the first excited state, you can get 2 excitons per, sorry, 2 triplets from a singlet. So it's called singlet fission. You're splitting the singlet state into 2 triplets. And you can design solar cells that have these singlet fission molecules present. And you need to have a second absorber here to absorb the light that's not absorbed in the singlet fission chromophore, because the transition from the ground state to S0 to the triplet is forbidden. So you've got, the transition is from S0 to S1, so it allows smaller photon energies, less than that energy gap, to be transmitted. So you need to pick it up in the second absorber. And the efficiency for PV would be about 46%. But what's interesting here, it's like a tandem cell, but you don't have to match the photocurrents like you do in a normal tandem cell, which is shown here for water splitting. So in a normal tandem cell, you've got to recombine a hole from one carrier, from one chromophore with an electron from the other to maintain charge neutrality, just like in a multi-junction solar cell. So this is being studied. There's many molecules that show this, and there's a nice review coming out in Annual Reviews of Physical Chemistry by Joseph Mickel and Millie Smith from CU, who we collaborate with. And we studied this molecule, which has a slip stack orientation in the crystal. And in this paper, we showed it has exactly 200% quantum yield. So it gives you right at the band gap of 2 times the HOMO-LUMO transition energy. It gives you 2 triplets, and these can be harvested in a solar cell. So maybe we should stop. These slides show that you need a Z. If you want to make fuel, you need two photosystems, just like photosynthesis. And that's a principle that's, I think, very general for all solar fuel producing systems. You have to mimic photosynthesis by having two absorbers, like in a Z scheme. And as a function of the overvoltage required, you get a much better behavior when you have 2 photosystems, even if they're not creating multiple excitons. So let me just conclude here. I'll leave that up, and during the question period you can read that. Thank you for your attention.